To the second session. What we have learned in the first session was the motion within constant acceleration of an object. There, we get to know about the three equations that are really useful in solving numericals. The first equation was V is equals to U plus AT. The second equation was X is equals to UT plus half AT square. The third equation was V square minus U square is equals to 2AX. Using these equations, we are going to solve a few examples to know the application of these equations and to better understand them in practical life. This is example number 1. Suppose a person goes on a morning walk in a semicircular park of radius r is equals to 50 meter. If he walks from point A of the park to the point B, find the distance covered by the person and the displacement of the person. As we can see that this is a semicircular park, thus the distance covered by the person would be is equals to circumference of semicircle. The formula for circumference of semicircle is equals to pi r, where pi is equals to 3.14 and is a constant in the formula, and r is the radius of semicircle, that is 50 meters. On product of pi r, that is 3.14 into 50, we get that 157 meters. This is the circumference of semicircle, and so the distance covered by the person while going from point A to point B would be 157 meters. The second thing that needs to be found out is displacement. What is displacement? Displacement is the shortest distance between the A and B. So, as we can see in the park, from point A to point B, there is only a one possible shortest distance, that is this straight line. Thus, the displacement done by the person from going from point A to point B is diameter of the park, and diameter of the park can be written as 2 times radius of the park, right? Where r is radius, which is equals to 50 meter. Thus, putting values on this formula, we get that 2 into 50 is equals to 100 meters. Thus, the final answers of the questions are the distance traveled by the person for moving from point A to point B is equals to 157 meter. Also, we can say that the displacement covered by the person from point A to point B is 100 meters. Let's get into the second example. The question is, an object starts from rest with constant acceleration. Okay, so this is the object and this is moving with a constant acceleration. Let's see how. At time t, velocity is u, that is 150 meter per second. So we got to know that initial velocity of the object was 150 meter per second. At time t plus 1, the velocity is v equals to 250 meter per second. That is the final velocity of the object achieved at time is equals to t plus 1 is 250 meter per second. We need to find acceleration and the distance traveled during the t plus 1th second. Okay, so how we are going to find it? What is acceleration? Acceleration is change in velocity with respect to time and is denoted by the letter a. change in velocity is final velocity, that is 250 meter per second, minus initial velocity, that is 150 meter per second. The change in velocity is 250 minus 150. With change in time is only 1 second, because t plus 1 minus t, that would be only 1. Thus, acceleration can be written as 250 minus 150 divided by 1, which would be equals to 100 meter per second square. This is the answer of the acceleration, the first part of the question, that is 100 meter per second square. The second part of the question was distance covered during the t plus 1th second, that is denoted by x, distance. Okay. So applying the third equation here, which was v square minus u square is equals to 2ax. Here v square is 250, actually 250 square of 250, since v was the final velocity. The square of v square is square of 250. U was the initial velocity, which was 150 per meter per second. So square of u is square of 150. So LHS can be written as v square minus u square can be written as 250 square minus 150 square. The RHS was is equals to 2ax. A is acceleration, x is the distance. Thus, we have already found out A is 100 meter per second square. That is our answer of the first part of the question. And x, we need to find it out. Therefore, 2 into 100 meter per second square into x. Thereby, by solving the equation, we get that x would be is equals to 200 meters. Further, let's get into the example 3. Example 3. So, question tells us about a ball. A ball of 5 kg mass was at rest before sliding on a 3.6 meter frictionless plane. The acceleration of the ball is observed as 5 meter per second square. We need to determine the change in velocity of the ball. So, the given things are initial velocity of the ball is 0 meter per second and is denoted by u, as it is already written as ball was at rest. Final velocity is denoted by v. Therefore, the change in velocity is equals to final velocity minus initial velocity. But since we have seen that the initial velocity was 0 meter per second, therefore change in velocity would only be equals to final velocity, that is v. Okay. So by applying the third equation of motion, that is v square minus u square is equals to 2ax, where they have their usual meanings. V stands for final velocity, u stands for initial velocity, a stands for acceleration attained by the object, x is the distance. Thus, in our equation, we are going to put numerical values. So v would be written as v only, v square, u is 0, so square of u is a square of 0, 2 is a constant, so 2 that has to be multiplied by a, which is 5 meter per second square as given in the question. X is 3.6 meter, since the plane that on which the ball has been traveling is of 3.6 meter frictionless plane. Thus, by solving this equation, we find out that v square is equals to 36, and by under root of the v square we get the value of v, that is the final velocity, which is 6 meter per second. Thus, as we need to know the change in velocity of the ball, therefore Initial velocity was 0, final velocity is 6 meter per second. So change in velocity would be is equals to final velocity, which is 6 meter per second. So this is our answer to the question. The next thing we are going to study here today is inertia. What is inertia? Inertia is a particle's state of rest or uniform motion along the straight line. We can try to understand this by using example. Okay. The first example, that is the tendency of a coin to stay at rest. Example 1 details as the coin placed on the card will tend to be at rest when card is stroked as coin will get into the glass. Let's try to understand this. Suppose there is a glass filled with water and a card is placed on the glass to cover it. Also, a coin is placed on the glass. Thus, as we stroke the card from a direction such that the card moves away from the glass, we will tend to see that the coin still goes inside the glass instead of moving with the card. This happens because of tendency of a coin to stay at rest. As we see that the coin was at rest before also, but as the card starts moving, the coin tries to stay at rest only. It doesn't try to move with the card. Although it was resting on the card, but it was not trying to move with the card. It was trying to be at rest and thereby it falls inside the water. The second example through which we can understand inertia is the football. Let's say the football tends to be in the motion while meeting the net when kicked. So let's say that a football player was kicking the ball into the nets. Thus, as the player kicks the ball tends to be in motion as long as it can be. Like it takes nets with the ball to a different position unless it stops. Thus, there comes a point in the nets where ball and nets move together just because the ball tends to be in motion and doesn't stop on facing the net. We could also understand this by the following example. Let m1 and m2 be the mass of two particles respectively and a1 and a2 be their acceleration. Referring to figures, we can see here that this is the particle 1 having mass m1 and acceleration a1. Similarly, this is particle 2 having mass m2 and acceleration a2. Suppose an equal force is applied on both. Then the acceleration of particles will never be same. Thereby, a1 will never be equal to a2. This is because a1 would never be equal to a2. Thus, this could be understood by if m1 is greater than m2, that is mass of first particle is greater than the mass of second particle, then acceleration of the first particle would be less than acceleration of the second particle. If the mass of first particle is greater than the mass of second particle, then the acceleration of the first particle would be less than acceleration of the second particle. Through this, we can understand that larger will be the inertia on acceleration 1, that is on particle 1. In the second case, we can make out that if the mass of first particle is less than the mass of second particle, then the acceleration of the first particle would be greater than the acceleration of the second particle. That is, smaller will be the inertia of particle 1 as compared to particle 2. Thus, it can be concluded that inertia is directly proportional to the mass of the body. That is, inertia is directly proportional to the mass of the body, as I have written this and as in mathematical way also. We can also refer to the figures. If the mass of the body is larger, the inertia would be larger. If the mass of the body is lesser, the inertia would be lesser. We can also refer the previous slide where the mass of the ball was greater than the nets. Therefore, the ball tends to be in motion and take nets with it. Otherwise, if the mass of the nets would be greater than the mass of the ball, then nets would have stopped the ball then and there, because the nets would be tend to be at rest, and that would have made the ball to be at rest as well. The next thing we are going to study today is Newton's law of motion. The Newton's law of motion. Newton has given three laws. The first is Newton's first law of motion. What Newton's first law of motion tells us that a body in a state of rest or in a state of motion remains to be as such until and unless subjected to an external force. This can also be said as if the summation of all the forces acting on an object is zero, then the particles remains unaccelerated. This is called Newton's first law of motion. Let's try to understand this using an example. An object of mass 0.30 kg is suspended from a string as given in the figure. An object A of mass 0.30 kg is suspended from a string. Then force acting on the object is equals to mass into acceleration due to gravity, where mass is denoted by m and acceleration due to gravity is denoted by g. Let's consider the g, that is acceleration due to gravity, is equals to 9.8 meter per second square. Therefore, by providing the values to this equation, we can write mass as 0.30 kg to the product of 9.8, that is acceleration due to gravity, equals 2.94 Newton. If object is at rest, then following shall be the condition, like pull from earth will be equal to pull from string, right? Pull from earth would be equal to pull from string. Therefore, the tension of the string would be also be equal to 2.94 Newton. Next, we are going to study Newton's second law of motion. The Newton's second law of motion states that the time rate change of the momentum of a body is equal in both magnitude and direction of the force applied on it. Mathematically, force is equals to mass into acceleration, or force can also be derived as a rate of change of momentum, where momentum is product of mass and velocity. Let's try to understand this through the derivation of momentum. Let m be the mass of the box. Here, this is the box of mass m, moving with a velocity u, and at time t is equals to 0, its velocity is u. When a force is applied from horizontal direction, then the box will attain a velocity of v at time t. Therefore, the initial momentum of the box would be mu, that is mass of the object into initial velocity of the object. Similarly, final momentum of the box would be is equals to mv, that is mass of the object into final velocity of the object. Therefore, change in momentum is equals to mv minus mu, and rate of change of momentum can be written as mv minus mu divided by time, that is t. Taking m is common from the above equation, we can write v minus u divided by t. We already know that change in velocity per unit time is written as acceleration and denoted as a. Therefore, the second law of motion can be derived to a point where F, that is force, is equals to mass into acceleration. The next thing that we are going to study is working with Newton's first and second laws of motion. For understanding the working of both the laws, let's consider an example. Consider a box of mass m pulled by a string by an angle phi on a table. So this is the mass of the box m, and it is being pulled by an angle phi. Let frame of reference be the box. Thus, force acting on the box are pull of the string T. This is the pull of the string T that would be acting along the string, that is along the string. The second force that would be acting is the Earth's gravitation force is mg, and that would act in vertically downward direction, in the direction of Earth. The third force that would be acting is the table's contact force. The contact force of table is, suppose, E, that would act vertically upward. So this is the free body diagram denoting all three forces with their directions. Tension force with an angle phi, Earth's gravitational force with the direction downwards with the box, downwards to the box, and contact force of table, that is E, which would act vertically upwards. To make the free diagram, we should consider three steps. That is, step 1, decide the system frame of reference. Okay, so first we need to decide on which frame we are going to find out the force acting on him. Step 2, identify the forces action on the object. So we need to identify like pull of the string, Earth's gravitational force, and the table's contact force. Step 3, make the free body diagram. So we made a free body diagram showcasing all the forces with their directions. Thus, along the x-axis, we need to find out the number of forces acting. So the tension force would have add the component T cos phi. How T cos phi has come here? Since it was acting with angle phi on the box and the force was T. So on an x-axis, it would make a component of T cos phi. Component of mg would be 0, since mg is acting completely in vertical direction, vertically downward direction actually. Similarly, component of force E would also be 0, because since it is acting in vertically upward direction, therefore its component on x-axis would be 0. Therefore, total force along the x-axis would be T cos phi plus 0 plus 0, that concludes to only T cos phi that has been acting along the x-axis. Using Newton's law, we can write that T cos phi is equals to ma. Therefore, T is equals to ma upon cos phi. Let's give this equation a name as equation 1. Thus, we need to also find out forces acting along the y-axis as well. Component of T, that would be T sine phi. How this has come? The box has been pulled by a string with the force T, making an angle phi with the table. So, T sine phi would be here or here. Component of the force of gravitation, that was mg. So that would be minus mg. And the component of E would be E, since it is working directly on vertically upward direction. Hence, the total force along the y-axis is equals to T sine phi plus negative of mg, that is minus mg, plus E. Also, we can put the value of T from equation 1 in this above equation. So, this equation can be written as E is equals to mg minus ma tan phi.